Okay, so we're now going to start with our development of free field theory in naught dimensions. And before we start, let me tell you why we are doing this. We're doing this to give you some intuition about how field theory in naught dimensions work. So especially when we start, I'm going to try to keep showing you the 3+1 dimensional formula and then how it works in naught dimensions. Once we've understood free field theory thoroughly, then we'll move on to the interacting field theory. Okay, so what do we want for free field theory? So this is my claim. So for free field theory, the action is quadratic in the field. So why do I say this? Well, this should be clear to you. If you work out the equation of motion, and what would you do? You would use the Euler-Lagrange equations. So if your action is quadratic, then the equation of motion is linear. If you have a set of linear equations, so linear in the field, this means the superposition principle holds. Okay, so that's my claim, which you can easily check. I claim if you write down any action that is quadratic in the field and you work out the equation of motion, you will always find that the superposition principle holds for that equation of motion. Good. So remember what things look like in 3+1 dimensions. Actually, I'm always going to write the 3+1 dimensional formulas in red and the naught dimensional formulas in black. Okay. So remember the action for the free field theory in 3+1 dimensions. Well, it was an integral d4x. We had 1/2 d mu phi minus 1/2 m squared phi squared. And you can see very clearly that things are quadratic in the field. When we come to naught dimensions, then the action will just be alpha over 2 times by phi squared. Good. Okay, then what was the basic formula of the path integral, the basic formula that we used? Okay, so basic formula was the following. We said that if you were to work out a time-ordered correlation function, so this is something very physical, you could relate it to an S matrix element and to a cross-section, which then could be measured at some accelerator experiment, okay? So time-ordered correlation function was given by an integral d phi e to the is phi of x1 up to phi of xn. So it was a path integral over the field phi. Thinking in terms of the time-ordered correlation function, you probably have a nice intuitive picture because you can imagine your field creating and destroying particles. So this would be some initial state is produced and then some final state is detected. And this can be related to some path integral. Well, in the naught dimensional example, we'll call our correlator phi n. Okay, so that's what replaces our correlator. And what will this be? This will be an integral over our field. So d phi. Phi can take values from minus infinity to plus infinity. We'll have e to the minus s, and we'll have phi to the n. And notice that this is a very, very nice integral because we're taking moments of a Gaussian integral, and that's a very straightforward thing to do. So now let's talk a little bit about the mechanics of the calculation. So how to do the computation. Well, I hope it's still fresh in your mind that what we did in 3+1 dimensions is we defined z of j, and this was equal to an integral, path integral, d phi. We had an e to the is, and then we had plus an integral d4x, j of x, phi of x. And if you remember, we generated our correlation functions by taking functional derivatives of z of j with respect to j, and then setting j is equal to 0. Well, in naught dimensions, we're going to do something very similar. We're going to choose z of j to be equal to, n is some normalization that we'll have to discuss in a minute. It's an integral from minus infinity to infinity, d phi e to the minus s plus j phi. Oh, and if I'm putting the normalization in here, I should really put the normalization in over here too. How are we going to fix n? So as follows. So first of all, how do we get phi n from z of j? Well, this should be very natural to you based on what you already learned in 3 plus 1 dimensions. So you'll take derivatives of z of j with respect to j, and then set j is equal to 0. And if we calculate the correlation function of 1, so remember what these correlators look like. They are, so this thing is what we would call phi of x1 up to phi of xn. So that means that if I just put a 1 in there, so no fields, that's just the overlap of the vacuum with itself, which we would set equal to 1. Okay, so that's the intuition that I want to take away. We usually set the expectation value of 1 to be equal to 1. So here, we're going to set the expectation value of 1 equal to 1, and this will fix the value of n. And then once we fix the value of n, we can calculate whatever correlator we want. Okay, good. Now, you have done all of these integrals previously, so I'm just going to give you some answers. I think that should be good enough. So let's first of all work out what is z with j is equal to 0. And you know that this is going to be the expectation value of 1 because we've taken no derivatives. So this should just be phi to the naught according to the green box formula. When n is naught, phi to the naught is just 1. And what will this be equal to? Well, this will be equal to n integral from minus infinity to infinity d phi e to the minus alpha over 2 phi squared. We've done this integral many times, so I'm just going to tell you the answer. It's n times by 2 pi divided by alpha square rooted, and that means that n has to be equal to alpha over 2 pi. So we have just fixed now the value of n. Good, that's our first result. So then what would z of j be? Well, z of j is equal to n, that's alpha over 2 pi, square rooted, integral d phi from minus infinity to infinity, e to the minus alpha over 2 phi squared plus j phi. And how would you do the integral? So do integral by shifting phi. So it would be a good exercise for you to see if you can do that, straightforward exercise. If you go ahead and do that, you'll learn that z of j is equal to e to the j squared over 2 alpha. So there's our second result. Nice explicit formula for z of j. Let me just make this clearer. This is really j squared. So that's j squared. Maybe that's clearer. Oh, sorry. Let me just... Now that's completely clear. So that's our second formula. This is what z of j is equal to. Good. Now, what do we use z of j for? To calculate correlators. So let's calculate a correlator. We want to calculate phi squared. Well, this will be a second derivative with respect to j of z of j evaluated at j is equal to 0. So let's go ahead and do this. This will be second derivative with respect to j of e to the j squared over 2 alpha at j is equal to 0. So we've got a d by dj, and let's take the first derivative. Well, the first derivative will bring down a j over alpha, e to the j squared over 2 alpha, evaluated at j is equal to 0. And if we take that second derivative, what do we get? Well, the d by dj acting on j over alpha gives us a 1 over alpha. But the d by dj can also act on the exponential, in which case it will bring down another j over alpha. So we get j over alpha squared, e to the j squared over 2 alpha, evaluated at j is equal to 0. So in the bracket sitting up front, when we set j is equal to 0, the second term vanishes. So the bracket just gives us a 1 over alpha. And then in the exponential, if we plug in j is equal to 0, we just get e to the 0, which is 1. So we found out that the phi squared correlator is just 1 over alpha. And I'd like to explain where that 1 over alpha comes from. Okay, so 1 over alpha comes from a pair of d by dj's. Okay, so the first d by dj produced j over alpha. The second then produced 1 over alpha. So the really important thing here is that the 1 over alpha comes from a pair of d by dj's and a pair of d by dj's is needed to produce something non-zero when we set j is equal to 0. See, one derivative is not good enough because it produces a j over alpha, and that vanishes when we set j is equal to 0. So we see that we need a pair of derivatives to act to produce this 1 over alpha. I really hope that this is ringing bells and it's looking very similar to what we did in 3+1 dimensions. We'll continue in a moment.